Students, in last lecture we learn wave optics, interference. For steady interference, what conditions are required, we studied in our previous lecture. In today's lecture we'll start with Brewster's law, and this is the last topic from the chapter, wave optics. Then we'll try to learn some example on this topic. Okay, we'll start. Sir David Brewster performed series of experiments on the polarization of light by reflection. By reflection. And in 1892 he discovered that when the light is incident on the transparent medium at a polarizing angle. Okay, here we know when light comes to a reflecting medium surface, it is partly reflected and partly refracted. Here Brewster's experiment is when light is incident at a particular angle to a plane boundary, the reflected light is completely polarized and refracted light is partially polarized. This angle is known as polarizing angle, or we can say Brewster's angle. So here is the statement: the tangent of the polarizing angle is equal to the refractive index of the refracting medium at which partial reflection takes place. Here uh, just I said reflected light is completely polarized and uh, reflected and refracted rays are separated by 90 degree. From diagram it is clear. This is the incident unpolarized light, normal, and plane polarized light is reflected in the same medium, and partially polarized light is refracted in the another medium. So this reflected and refracted light makes 90 degree, or they are perpendicular to each other. So according to the Brewster, once again, when unpolarized light is incident at a particular angle, then reflected light is plane polarized light and refracted light is partially polarized. The angle at which the reflected light is plane polarized light angle is known as polarizing angle, or simply you can say Brewster's angle. Very simple. IP, angle of polarization. We know that angle of incidence and angle of reflection is same. Mu is the refractive index of the medium. Now proof is very simple. We know that this is the straight angle. Okay, so it is 180. Reflected angle is IP. This is 90 degree, and here is RP, refracting angle. So we'll write 180 degree is equal to angle of reflection, angle of incidence and angle of reflection will be same, 90 degree plus RP. Rearranging the terms, we'll write uh, angle of refraction RP is equal to 90 minus IP. This 90 to this side, 90 degree will be remain, and IP it becomes minus IP, therefore RP is equal to 90 degree minus IP. We know the Snell's law, mu is equal to sine IP by sine RP. RP is 90 minus IP. So here RP is replaced. But we know that sine 90 minus IP is cos IP. Okay, so mu is equal to sine IP by cos IP, and this is mu is equal to tan IP. So here it proves the statement of the Brewster's law. Tangent of the polarizing angle is equal to refractive index of the refracting medium. So this mu is equal to tan IP. This proves the Brewster's law. And here our theoretical part is end. Now we'll discuss some examples. First example, white light consists of wavelengths from 400 nanometer to 700 nanometer. What will be the wavelength range seen when white light is passed through glass of refractive index 1.55? Here light is passes from one medium to another medium. Okay, and uh, given is refractive index of the glass medium is given, and smallest wavelength is 400 nanometer, uh, largest wavelength is 700 nanometer. Then uh, range of wavelength of the light when passes through the glass has to be determined. So we know that a refractive index is equal to wavelength of the light in the air medium or vacuum to the wavelength in denser medium ratio. So we'll rearrange this. We already studied this formula in 11 science. Okay, then smallest wavelength in glass is 400. Okay, uh, this question 2.5806 into 10 to the power 2 nanometer. By shifting the decimal point, we'll write 258. Unit we'll keep as it is, nanometer. Then for largest wavelength, again the formula, same formula, and largest wavelength is now 700 nanometer. So after calculation, we'll get 4.5161. This calculation you can do by using logarithmic tables, and we'll get 451.61 nanometer. So this is about the shortest and the longest wavelength. Next example is the intensity of the light coming from one of the slit in Young's experiment is twice the intensity of the light coming from the other slit. What will be the approximate ratio of the intensities of the bright and dark fringes in the resulting interference pattern. Again, this example is on Young's double slit experiment. From this experiment, we obtained two coherence sources. So we'll go according to the statement given is I1 is equal to twice of I2, and we have to find what the ratio of uh, maximum intensity and minimum intensity. So we know the formula, ratio of maximum and minimum intensity. It is I1 root I1 plus root I2 bracket square, addition of intensities of the light uh, is the maximum, and subtraction of the intensities. Okay, so here we have to use, instead of I1, 2 I2, twice of I2. So this becomes root 2 I2 plus root I2 bracket square. Instead of I1, use twice of I2. Then after solving this, we'll get root 2 plus 1. Here I1 plus I2 is equal to, if the intensity is the same, we'll write this, and we'll get 2 plus I plus twice of root 2. 2 plus 1 is 3, and this bracket, according to A plus B bracket square identity, will write 9 plus 8. Okay, this square is 4 into 2, so 8. 3 square is 9, and 6 into 2 is 12 root 2. Using value of root 2, that is 1.41, we'll get 33.96, approximate it is 34, or nearly equal to 34. So the ratio of the maximum 34. Okay, next example is in double slit arrangement produces interference fringes for sodium light. Wavelength is given, it is 589 nanometer, that are 0.20 degree apart. Fringes are there in sodium lamp. Wavelength is given, and fringe width is this. What is the angular fringe separation of the entire arrangement is immersed in the water? Refractive index is given, that is 1.33. Double slit arrangement, interference fringes, and light is used, sodium light. Wavelength is given and separation is given. When the assembly is in the water, then we have to find out the separation between the fringes. Lambda wavelength is given, theta angular separation given when the assembly is in vacuum, and refractive index of water is given. We have to find out angular separation when arrangement is dipped in water. Formula, theta is equal to lambda by A. Actually it is sine theta by lambda. uh, Sine theta is equal to lambda by A. Theta is very small, it is 0.2 degree, so instead of sine theta we have to consider theta. Then theta is 0.2 degree uh, is equal to lambda. Then we'll write 589 is equal to 0.20 degree into E. Now lambda dash wavelength in water will find using this formula. Lambda dash is equal to this. Okay, lambda is equal to this, that is 0.20 degree into A. Now 1.33 is 4 by 3, 4 divided by 3, so 3 is to the numerator. This is 1.33 is replaced by 4 divided by 3, 3 is in numerator, and we'll get it is 0.15 degree into A. Then again we have to use the formula. Lambda is 0.15 degree, A cancels. So when assembly is immersed in water, the angular separation between the fringes will be 0.15 degree. Again, one more example is on double slit arrangement. In a double slit arrangement, the slits are separated by a distance equal to 100 times the wavelength of the light passing through the slits. What is the angular separation between the central maxima and an adjacent maxima? What is the distance between these maxima on a screen? 50 centimeter from the slit. Two different questions are there, double slit and diffraction. Angular separation between the central maxima and adjacent maxima has to be found out, or secondary maxima, and distance between maxima on the screen. Distance, okay, when distance is between screen and slit is 50 centimeter, then what is the distance between the central maxima and secondary maxima? Given is d is equal to 100 lambda. The statement is the distance separated by a distance equal to 100 times the wavelength. So small d is equal to 100 into lambda, and capital D is 50 centimeter. We have to find out angular separation between the central maxima and the adjacent maxima, and distance between maxima. Angular separation and distance between the maxima has to be found out. So theta is equal to lambda by d, and here lambda by 100 lambda, lambda cancels, 1 divided by 100, so it is 0.01 radian is the angular separation between the uh, maxima and adjacent maxima or secondary maxima. Then distance between maxima, it is lambda capital D by D. Lambda divided by D is theta, and theta is 0.01 and D is 50. So simply 0.01 into 50 is equal to 0.5 centimeter. So distance between the maxima, that is central maxima and secondary maxima, is 0.5 centimeter. Next is the distance between two consecutive bright fringes in the biprism experiment using light wavelength 6000 angstrom in it is 0.32 millimeter. by how much will the distance change if light wavelength is 4800 angstrom unit is used. Here source is changed. Then we have to find out the width of the band. Distance between consecutive bright fringes is given. It is 32 millimeters. So we'll write 10 to the power minus 3 meter. And first time wavelength is 6000 angstrom unit. So we'll write 6 into 10 to the power minus 7 meters. And second time source is replaced and wavelength is 4800 angstrom unit. So we'll write 4.8 into 10 to the power minus 7 meter. So let uh, we have to find out the change in uh, distance between the fringes, that is lambda a ya minus yb. Okay, yb be the distance consecutive bright fringes when wavelength is lambda b. Similarly, we can say when uh, wavelength is lambda a, the distance between the fringes will be lambda a. So this difference has to be found out. So we'll write lambda ya lambda b. Theta is equal to lambda by d. Here we'll write ya. It is the distance. So definitely it is lambda a, sorry, ya lambda b is equal to yb lambda a. So yb is equal to ya lambda b by lambda a to this side, and using the values, lambda a is 0.32 into 10 to the power minus 3, and yb is 4.8 into 10 to the power minus 7, and divided by lambda a is 6 into 10 to the power minus 7. So after solving this, we'll get 0.265 into 10 to the power minus 3, that is 0.256 millimeter is the uh, distance between the fringes when the light is replaced by uh, the wavelength 4800 angstrom unit. Next example, or we have to find out this ya minus yb. Ya is 0.320 into 10 to the power minus 3, and yb is this 0.256 into 10 to the power minus 3. So subtraction will give us 0.064 into 10 to the power minus 3. So change in distance is 0.064 into 10 to the power minus 3 meters. It is in mm. 10 to the power minus 3 is replaced by millimeters. Now next example is the optical path of a ray of light of a given wavelength traveling a distance of 3 centimeter in flint glass having refractive index 1.6 is same as that on traveling a distance x centimeter through a medium having refractive index 1.25. Determine the value of x. Optical path of the ray light traveling a distance 3 centimeter in the flint glass having the refractive index 1.6 is same as that on traveling a distance x centimeter through a medium having refractive index. Okay, refractive index is means medium is changed. Then we have to find out the distance, what distance is traveled by the wave. Here d1 is equal to 3 centimeter, n1 is 1.6 and n2 is 1.25. We have to find the optical path in the medium 2, that is d2. Formula is n1 d1 is equal to n2 d2. Okay. So we'll write value of n1. This is on optical path, and the optical path lambda is equal to n d. We already studied in our theory lecture. So same we have to use over here in comparison. Uh, Here d2 is the distance traveled by the uh, blue or traveled by the light in flint glass when refractive index is 1.25. So d2 is equal to 1.6 into 3 divided by 1.25. Simple calculation will get 3.84 d2, and the distance traveled by the light in the medium whose refractive index is 1.25. Next example is in uh, Fraunhofer's diffraction by a narrow slit. A screen is placed at a distance of 2 meters from the lens to obtain the diffraction pattern. Distance between screen and the lens is given. If the slit width is zero point 0.2 mm and the first minimum is 5 millimeter on either side of the central maximum, find the wavelength of the light. Fraunhofer's diffraction, single slit, and here distance between lens and the screen is 2 meter. Okay, and width is 2 mm. First maxima is at 5 millimeter either side of maximum. We have to find out the wavelength. So given is d, capital D is 2 meter, width is zero point 0.2 millimeter. We will write 2 into 10 to the power minus 4 meter. Then distance is 5 millimeter. Width of central maxima 2 into 5 mm. Okay, so this will be gives us what, 10 mm, 10 into 10 to the power minus 3 meters. So what has to find out, wavelength find out करना है. Formula has to be used for the central maxima, width of the central maxima. We already studied in our theory. Width of the central maxima is 2 lambda d by a. A is the width of the slit and d is the distance between the slit and the screen. Okay, we know that uh, to determine the width of the central maxima, lens is close to the slit. Therefore, here the distance given between lens and the screen. Okay. So we'll rearrange the or use the values and rearrange the equation. Width is given. It is 10 into 10 to the power minus 3. Lambda as it is. D is 2 meter and A is uh, uh, slit, width of the slit, it is 2 into 10 to the power minus 4. So lambda is equal to, we'll write 10 into 10 to the power minus 3 into 2 into 10 to the power minus 4. This 2 into 10 to the power minus 4 to this side, and 2 into 2, that is 4. So this calculation gives us what, 5 into 10 to the power minus 7. If we convert this in the angstrom unit, so we'll write 5000 angstrom here. So this is the wavelength of the light used in Fraunhofer's diffraction. What must be the ratio of the slit width to the wavelength for a single slit to have the first diffraction minima at 45 degree? So it is again on single slit experiment, and angle is given 45 degree. So 45 degree will write pi by 4 in radians. We have to find out ratio of slit width of to wavelength of the light used, A by lambda. Okay, theta is equal to lambda by A, and theta is 4 by pi by 4. So if reciprocal, A by lambda is equal to 4 by pi. Okay, pi is 3.142, and we'll get 1.27 is the ratio of slit width to the wavelength of the light. Slit width is A and lambda is the wavelength. This ratio is 1.27. So this is the examples which are included in our syllabus. We'll stop here. Thank you.